All right, it's doing it. Okay. So we were just graphing out the situation of a spring pendulum, and we're going to imagine that it's a dual spring pendulum. Okay, so springs on either side, and we have simple harmonic motion where this mass is being oscillated back and forth. So the first thing we'll do here is we'll just look at, well, we mapped out where it is in terms of position versus time. Delta x here being its displacement from its neutral position. And we just called it as having a maximum of 1, so the amplitude of 1. And we just wanted to reference back to an object spinning around a circle and map where that object is in time. Okay, this one has a period of 1 second, so you have one complete oscillation every second. And we looked at its velocity graph, which, you know, if this maps to a sine wave, then this maps to a cosine wave. Being that as it passes through the middle, it's going to have its maximal velocity. All right, so here at position 1, it's got its maximum positive velocity. It's on its way up. As it travels upward, it slows down to 0 when it's at its max upward displacement. Okay, then it zips back down the opposite way, so then it'll have its maximum negative velocity as it passes through neutral, and so on. So if this maps to a sine, then this maps to a cos. And then the forces involved, okay, well, they're maximally down or maximally negative when this is maximally positive in terms of position. There is no force, or no net force anyway, as the object passes through 0 or through its neutral position. The up and the down pulls of those springs have canceled each other out, and so on. So if this is a positive sine wave, this is generated by a negative sine wave. Okay, and so we're mapping position and imagining that the object is, you know, essentially its position is like a shadow of the radius as the radius rotates around the circle. That's what we're sort of doing with our delta x, and then this is doing our cosine of that value, and then this is the negative of that value. So where we're getting to now is we want to know what's happening in terms of kinetic and potential energy. So the first thing we got to do is remind ourselves what those terms mean. So potential energy in this case, and we'll call this a double spring system. Okay, so in what form do we find our potential energy in a double spring system? Anybody know? So here we are, right? Now let's just imagine we're looking down at this from above. Okay, and this is, you know, this object is oscillating back and forth between two fixed points on two large springs. Okay, and if I move this all the way here, okay, or if I allow this to start oscillating, it's, you know, undergoing SHM and bouncing back and forth. Right here, what's the velocity of the object? 0, right? 0 meters per second. Okay, and if I look, I've got this spring stretched to its maximum, right? So I would have, at this point, a maximal downward force, right? If you remember, F is proportional to K times X, and actually that's negative. So whichever way the spring is stretched, so if it's stretched positively, we have a negative maximum force there. Anyone remember whose law that is? Who came up with this idea about springs? Yeah, Hooke. Excellent. That's Hooke's law. Okay, it says if you stretch a spring, the farther you stretch it, the larger the amount of restoring force it's going to present to you. Okay? All right, and then at this point here, right, we have an equal up and down spring force. So anytime this object is at its neutral position, the net force at that point is equal to 0. Okay, so 0 force. And we would also say then the potential energy. The potential energy at this point is 0. right? Potential is 0. There's no stored energy in those springs, right? They're equally pulling on each other. If I came back in 100 years, this object would still be sitting exactly where it was. Okay, there's no potential energy when I have equal spring forces pulling opposite to one another. Okay, but what I do have at this point is maximal what? Well, I got my maximum velocity. Okay, so potential energy in a 2-time spring pendulum is, well, it is stored as elastic potential. So stored as elastic potential energy, right? Anytime I stretch something, I did work to stretch it. I had to work, I had to apply a force over a distance to stretch that object out, storing energy in it, okay? And we can also say kinetic energy is present when a mass is moving. All right. So say E sub k, the energy of kinetic energy, or kinetic motion, the energy of motion is 1/2 mv squared. So it's going to be maximum in this case when velocity is maximum. And elastic potential energy is equal to 1/2 kx squared. So it'll be maximum when we have the largest delta x, the largest amplitude. All right. Now, it's a little trickier here when we want to draw the interaction between these two things, because I think you can probably imagine in your mind that there's going to be some sort of oscillation between these two situations, okay? So to kind of, I wonder if I still do. I still have this saved here. I want to draw this. Yeah, perfect. Uh-oh. Should group this. Group it. There we go. Perfect. All right, so to help us out, I can cheat a little bit here and I'll pull in a couple things. We're going to start fresh here with our map of the oscillation, right, in terms of position. I don't know why I just drew that there. I'll put it here. Okay, and we'll call this time. All right, so we have 4 seconds, 4 oscillations. All right, what I'm going to do is I'm going to put in here a little axis, and what we're going to try to do is we are going to try to map out or figure out how these two energy systems interact. Now, one thing that's not interesting, but to keep in mind, is that you cannot have negative potential energy. It's not a vector value, right? You can have 0 or you can have some. You can't have negative. So one thing we'll do here is we'll mark out the total energy of the system. Now, the total energy of the system obeys the law of conservation of energy. So the total energy of our spring pendulum system is always going to be constant, isn't it? Now, this is theoretically constant because in the real world, you're going to lose energy. It's going to leak off into the environment, right? But for our purposes, just at first here anyway, theoretically, we have this situation. So let's just look at our first 4 seconds. Actually, yeah, I guess we'll have to look at 4 seconds. Okay, so I better make this a bit bigger. Stretch this out a little bit more. Okay, and let's call EK be the blue line, and we'll say EE be the white line. I don't like that. Let's make it like red. Okay, so let's try to map out our EK here first. So I'll make some points. Here's 1 second, 2 seconds, 3 seconds, and 4 seconds. All right, so at the beginning, right here, at the start, we're going to have a maximum value for kinetic energy. This object is at its max upward velocity, right? I'm also going to draw in some sublines here just to help us mark where we're at. It's going to get a little bit messy. Okay, 1, 2, 3, 4 seconds. Okay, now at what point is kinetic energy going to be 0 for the first time? Well, when I get to here, right? When this thing is maximally displaced positively, it turns out that my kinetic energy will have dropped to 0. Correct? 0 E. Okay. And then when I get to here, I'm back to max EK. Yes, it's downward, but remember, kinetic energy is always positive. There's no such thing as negative kinetic energy. Here again, it's at 0, and here again, it's max. So that presents us with a bit of a difficulty because this is going to be oscillating, and it's going to have a frequency that's double that of our initial wave, right? Because it maxes out every single time our other object passes through the origin, okay? So by the time we get to half a pi, which I'll represent here, this is pi, this is 3/2 pi, and this is 2 pi, okay? By half a pi, EK is supposed to be blue. EK has dropped to 0. And then by the time I'm back to here again at pi, or in a circle, right? I've gone halfway around the circle. By the time I get back to there, I'm now back up to maximum, minimum, and by the time I get back to where I started, I'm at maximum again, okay? This is an important feature. It shows you that energy changes, if I focus on one of them, happen at twice the frequency that displacement changes happen or velocity changes happen, okay? Now, it's not easy to draw this like perfectly, but this is going to continue on for my whole 4 seconds. I'm not going to bother to draw it all in, but it will continue, okay, to do this. So I'll just draw an arrow to say that keeps on going. Now, what else is going to happen? At the same time, okay, when I'm at my beginning, right here, spring potential energy is 0. There's no stored energy in the springs at this point. It's all in kinetic energy, right? We got maximum motion here. And then when we get to here, at half pi, we've maxed it out. So we're going to get that, that, and so on. And if you think about it, the sum of these two things will always sum to a total amount of energy, our theoretical total energy for this system, whatever it may be, okay? So if you add these two things together, you always come out to being the green line. If I've drawn this perfectly, that is, and clearly I haven't, but maybe we could we do it in here maybe? Okay, so there's our object. Now what if we were to go, okay, I don't know how do I move it just up to never having a negative value? I have to go absolute value there, right?
+1. Let's go +1.
You sure? Yeah. Can I do that? Oh, yeah, good call, Sonny. Yeah, yeah, right. I think I gotta bracket it up though.
But if you did get it, it would also still be, yeah.
No, I don't think that would help. There we go. Okay, perfect. So we're getting closer. Now I gotta double it. I gotta double it, right? I gotta double the frequency of it. Oh, so I gotta do that in here, I think, right? Okay, there we go. We're getting there. Okay, I also have to move it over to the side one. How do I do that? This? No. Oh no, that's not how I do it. I gotta make it a cos.
Yeah, I was gonna say, if you're trying to change.
I'll make it a cos. There we go. Okay, now what I can do is I think I can do the same thing. I can add another expression right over top of it. But I got to invert it. Yes! Okay.
Pretty convenient.
Yeah. I don't know if I picked the right colors for the right ones, but let's snip that and drop it in here so you have it for posterity. Well, the numbers are going to be maybe not what you'd expect, I guess, but I mean the concept is there, and it's just it'll make a nicer picture than what I drew. Yeah. Sure. Okay. So with elastic potential, if we look here, okay, when I have two springs, so imagine I've got I don't know, can't think of anything. So I got my mass here, right? And I got a spring on this end and a spring on this end. And let's say like we're sitting on a tabletop. We're sitting on a surface with zero friction, okay? If I let the thing come to rest, it'll sit right in the middle. Okay, it could have a little bit of force pulling it either way, but let's just say it doesn't. The springs are completely relaxed. Okay, so they're fixed. Now I take the object and I pull it to the side. I'm stretching the spring, right? As I stretch the spring, I have to do work. So I'm moving it to the side. I'm pulling on that spring, moving it over. That is storing energy in that spring, right, as I stretch it. Okay, if I release this object, that spring is going to cause an acceleration back towards the way it's pulling. We're going to pass through neutral. Okay, and now the motion of that object is going to stretch the spring behind. Now we're storing potential energy in the spring, causing a force back in the other direction. Okay, when I hit the middle though, when I'm right in the middle, when my velocity is high, the spring force is zero. The net spring force is zero. Okay, so what you end up with then is you end up with this oscillation between kinetic and spring forces acting. Oh, and actually it did work out. Or, oh no, sorry, it didn't. To flip this over to make it match. There. Now it matches. Okay, at the beginning, right, the object is at maximum upward velocity. It's at maximal EK right here. Okay, and it's at zero spring potential. Okay, and this line across the top, we can pretend what that represents is the total energy of the system, which will always be the sum of these two things, right? If we look at here, let's say we've got half of our energy from spring and half of our energy from kinetic. Here we've got all of our energy from kinetic, but the sum of those two, and zero from spring, the sum of those two values always adds up to the total energy of the system. The total energy of the system is always the same, okay? So the points along these graphs, if you sum them, if you add them together, you know, they're always going to add up to the expected result, right? If we say 1, 2, 3, and 4, no matter what, if I look down at any point, the sum of those two things is always going to be equal to 4, okay? That's just a random arbitrary number, but in real life, this is kind of how this would shake out, okay? Are there any questions about that? Is it making sense to you? Do you understand why the oscillation of potential and kinetic energy is double the frequency that the actual motion of the object is? Do you understand that? Does that make sense? Again, just to remind you, the reason why is because you get max velocity, max velocity, max velocity during one oscillation. In other words, the rate of hitting max velocity, okay, is twice the rate of the oscillation itself because you pass through the middle. And you never have negative kinetic energy. There's no such thing, right? You're either moving and you have energy or you're not. Direction does not matter in terms of potential energy. And same with spring energy. Direction doesn't matter. You either can do work with your spring or you can't. Yes, obviously when it applies a force, that'll be a vector value, but you can take a compressed spring, move it to a new situation, and you haven't changed the amount of energy that's in it. Okay, you have not changed the amount of energy by orienting it differently. Okay, I think I'm going to end there. That's probably like enough on this topic. There's a lot more like mathematical tie-ins you can do if you're interested. If you want to try to like create functions that tell you, say, when exactly this object is going to be, or where it is at specific points in time, let's say. So where is it, at, 3/8 of a second or something like that. You can work that out if you want to like go tangle with the math a bit. But this is a nice place where stuff that comes from the world of math jives really nicely with actual phenomena in the real world. Okay, and that's kind of where physics comes in, right? It's learning to speak math about the real world. So the better you are at math, the better these connections are going to be. And hopefully seeing something like this, actually observing a bouncing pendulum in real life, pulling, graphs like this off of, your graphing software, actually seeing that thing bounce and draw out a perfect sine wave for you helps these connections all kind of make sense. And that's really the goal at the end. Okay, done.